Hey everyone, and welcome to This Explainer. Today, we're basically playing the role of scientific detectives. We're going on an investigation to uncover the invisible, fundamental materials that literally make up our entire world. It's so easy to just look around and assume we understand exactly what things are made of. But honestly, the physical world is incredibly good at keeping secrets. Think about this for a second. How do we actually know what's inside a sealed parcel if we're absolutely not allowed to open it? Just like a heavily taped cardboard box, matter really hides its true nature from us. We can't just peer inside a single atom or a molecule with our naked eye. So instead, we have to use these really clever indirect experiments to deduce exactly what our world is made of. We have to hunt for clues. Okay, so here is the 5-part roadmap we'll use to crack the case today. First, elements versus compounds. Second, forging a new compound. Third, the true nature of mixtures. Fourth, invisible mixtures around us. And finally, thinking like a scientist. Let's get to it.
Part 1, elements versus compounds. Let's start right at the beginning, looking at the basic, unmixed ingredients of the universe.
So, meet our 2 primary suspects for today's case. And wow, notice the sheer contrast between them. First, we have sulfur, which you might see being mined right out of a steaming volcano crater in Indonesia. Sulfur is a nonmetal, it's bright yellow, super brittle, and it absolutely does not conduct heat or electricity. Oh, and it's completely non-magnetic. Then we have a totally different suspect, iron. Picture a blacksmith hammering away at it. Iron is a metal. It's hard, it's gray, it's incredibly strong. It conducts heat and electricity brilliantly, and crucially, it is highly magnetic. So we've got 2 completely different elements with completely different personalities.
Moving on to part 2, forging a new compound. Now we're going to see what happens when we force these 2 very distinct elements to interact under intense heat. This right here perfectly captures the magic of chemistry. When we take that iron and sulfur and crank up the heat in a boiling tube over a Bunsen burner, something incredible happens. Those independent yellow sulfur atoms and the orange iron atoms literally lock together. They bond tightly. They're no longer independent elements anymore. They've actually combined to form a completely new chemical compound called iron sulfide. Now, this is a massive scientific twist, so pay attention here. We need to understand the fundamental difference between just mixing things together and actually creating a chemical compound. Unlike a simple physical mixture where the ingredients just kind of sit next to each other, our new compound, iron sulfide, loses its original properties entirely. The rules have completely changed. That means the iron bonded inside this new compound, it's no longer magnetic, and there is no way it's conducting electricity anymore. To really prove this distinction, let's look at what happens if we skip the heat entirely. If we simply take iron filings and yellow powdered sulfur and just stir them together in a beaker, they haven't changed chemically, right? They remain a simple physical mixture. And because they keep their original properties, we can completely exploit that to separate them. You just grab a regular horseshoe magnet, hover it over the mixture, and boom! You pull those dark iron filings right back out of the sulfur. The iron is still magnetic because, well, it hasn't bonded to anything. All right, part 3, the true nature of mixtures. Let's shift our focus to everyday substances that look completely uniform to us, but are actually hiding a complex mix of ingredients. But before we investigate further, we really need to get our terminology straight and bust a very common myth. In everyday life, we might call a fruit juice pure just because it doesn't have artificial additives, right? But in science, the strict definition of pure means a substance contains only a single substance, with absolutely nothing else mixed into it, period. If it has even one extra type of atom or molecule floating around in there, it is technically not scientifically pure. Which brings us to part 4, invisible mixtures around us. Armed with this super strict definition of purity, let's investigate 2 essential things we interact with every single day: the air we breathe and the water we drink. Let's start with the air. It looks clear, it feels uniform, but guess what? The air around us is not pure at all. It's actually a dynamic, ever-changing mixture. It's mostly composed of nitrogen, a massive 78%, followed by 21% oxygen. And that remaining 1%, that's a fluctuating mix of carbon dioxide, argon, water vapor, and a few other gases. The exact makeup is actually changing all the time based on the weather and our environment. For instance, carbon dioxide levels go up and down based on natural emissions, like plants and animals breathing, and of course human activity, like burning fossil fuels. If we zoom all the way in to a microscopic level,
you can clearly see these different elements and compounds just floating independently in the air. You've got paired nitrogen molecules, paired oxygen molecules, and the slightly more complex carbon dioxide and water molecules. The absolutely crucial thing to notice here is that they're bumping around, sure, but they are not chemically bonded to each other. That total independence, that is the absolute hallmark of a physical mixture.
Similarly, a glass of crystal clear mineral water is an absolute master of disguise. I mean, it looks like pure H2O, doesn't it? But if you take a quick look at the typical analysis label on the back of any bottle, it proves that it's actually a really complex solution. It contains dozens of dissolved minerals. Just looking at a typical label, you might see 55 milligrams per liter of calcium, a whopping 248 of bicarbonate, 37 of chloride, and 24 of sodium. Because these minerals are just dissolved in the water and not chemically bonded into some new single liquid compound, mineral water is definitively a mixture.
So how do we actually prove it? Well, to uncover this invisible mixture for yourself in a lab, you'd run a super simple evaporation experiment. You just put some of that mineral water into an evaporating basin, heat it over a Bunsen burner until it boils, and then just let the water slowly turn into gas and escape. And what happens? The water leaves, but the dissolved minerals cannot evaporate. So once the basin cools down, you are left looking at this solid, crusty residue right there in the dish. The mixture has been successfully separated.
Finally, part 5, thinking like a scientist. So what does this all mean for us?
We've bonded iron and sulfur, we've dragged magnets from mixtures, and we've basically boiled the invisible minerals right out of our drinking water. And it brings us right back to our original problem, the mystery parcel dilemma. You see, scientists are constantly faced with a massive conveyor belt of sealed boxes. They can't just see or touch the tiny invisible particles they're investigating. They can't look at a chunk of iron sulfide and literally see the tiny bonds between the atoms. Instead, they have to use whatever information is available. They have to heat things up, try to separate them, test for magnetism, evaporate liquids, all to deduce exactly what is hiding inside that box.
Because scientists have to rely on these really clever deductions and indirect experiments to understand our chemical world, it leaves us with such a fascinating perspective to take into our everyday lives. Seriously, look around the room you're sitting in right now. What hidden mixtures and invisible compounds are right in front of you at this very moment? The screen you're watching this on, the drink on your desk, the very air you're breathing as you listen to this, it's all just one giant complex chemical puzzle, just waiting for the right detective to figure it out. Thanks so much for joining me on this explainer, and hey, keep questioning what's inside the parcel.